From now we have to say former RGS developments, and now you have Therma-G.
Therma-G, yes.
Therma-G, yeah. Energy everywhere. You have to advertise for them a bit. And yes, Anir is the head of technology now, and the floor is yours.
Sure. Thank you, Amit. So yes, I think now moving from the materials to more application-oriented talks. I'm Anirudh Hare. I lead the technology team at Therma-G, which was formerly called RGS Development. And in our company, we focus on getting the materials and maturing the processing as well as the integration into devices, always with a view of what is the end use, right? So we trace back from there what the requirements are for such materials, as well as the interfacial layers itself. So in this talk, I'll give you this industrial perspective. But before that, a bit of history. So RGS was founded at the TNO, ECN, which is the Energy Center of the Netherlands. It is based in Petten in the north, and that is also where we are, north of Amsterdam, 45 minutes away. And in 2005, the company was founded because we figured out a method to make direct wafering technology. So we started with silicon wafers. And as you know, silicon typically was made with the Czoralski method, where you make these ingots and you do the slicing, and you lose a lot of material in this slicing. So the idea was to go into the direct casting of wafers, thin wafers that can be used in photovoltaic devices. So that was the history. Since then, we started branching out into other silicon-based alloys. And one of the materials that we focused on was the silicon germanium, where we make this architecture based on silicon germanium materials, so both P and N doped silicon germanium, that we put together into such an architecture for applications up to 800 to 1000 degrees centigrade. So here we worked on the material, we worked on the bonding, we also worked on tailoring the architecture for the incoming heat flux densities. Since then, at Therma-G, we have been looking at integrating such devices, solid-state heat-to-power conversion technologies in various applications. So heat-to-power in boilers, as well as RPS, which are radioisotope power systems for space powering applications, as well as industrial waste heat. So here you can see a steel slab, which is at 1000 degrees centigrade, as well as our panels, which are on top of them. So really harsh environments and really harsh temperatures also. Before we delve into how we make these kind of products, since this was also a workshop, the idea was to go into, okay, how do you make such devices, and what is important besides the material itself to make such a product? And after that, I will go into the two main applications that we use to drive our development within the company, and that is the why we exist, right? What is the final application which leads to the requirements for our device and material itself? So, some theory. I think we have already seen this graph quite a few times already, where we know that in the active material, in the TEG, there are quite a few material properties which are important. So there's a seebeck, there's electrical conductivity, as well as the thermal conductivity. And all these three material properties are both temperature as well as dopant dependent. You see with temperature, all these materials perform well at various temperature zones. And that's why you want to use them in those temperature zones. And then you look at the dopant dependency. Patricia already talked about it. If you want to optimize the ZT, which is the combination of all these three elements, three properties, you can get to a maximum peak ZT. But from a device perspective, peak ZT is one thing, but what we are most interested in is the average ZT across the temperature of operation, right? So that's what you want to look at from the active thermoelectric material. But besides the thermoelectric properties, what we found were even more relevant for our use case were the mechanical properties. So if you want to use these materials as well as make sure that they function through their operation, the Young's modulus, the hardness, the fracture toughness, these are all material properties that we have characterized, as well as the coefficient of thermal expansion. So you need both the N and the P, typically from the same material class, so that they expand in a similar way. And that's something why we also look at an all silicon germanium based module. We do not try to mix two material classes. So these are some of the properties which are relevant for the material that goes into a unicouple, but then you have to put it all together. So you also have the interfaces between these materials, as well as the top and the bottom end connectors. So that's what is basically transporting all the current through the entire device. And there, the thermal expansion coefficients of the interfacial layers, as well as your materials that you use for the active material and the end connectors plays a role. And from an electrical point of view, the electrical contact resistances, I think that's something that was also previously mentioned in the morning. The bonding method and the diffusion barrier layers play a big role. So what is the contact resistance that you end up with? Here you can see, in the beginning, if you can have your conversion efficiency, which if you simulate it, you build it, you get a really high, 5 to 7%. But then if your contact resistance is high, that can drop dramatically. So you can get a loss of 50% in your conversion efficiency. So going from material to technology, you need to work both at the interfaces as well as the bonding, right? Bonding to the end connectors. So they are equally as important as the TEG active material itself. So now we have a unicouple. So from the unicouple, now when we go to the device, now zooming out, what you see is that how do you get the heat in and the heat out? So that's where the thermal coupling to the device itself starts to play a big role. So depending on what kind of application you have a conductive heat transfer, a convective, or a radiative. Each one of them has its own characteristics. So in the contact resistance, the roughness of the surfaces start playing a big role here. You want the heat transfer coefficient to be as high as possible. Similarly, in the convective one, depending on how are you channeling the fluid, right, on the hot side. Is it a passive flow? Is it a forced flow or a liquid? And then on the radiatively heat transfer, you have the view factors. And that also, in the space applications, may make a lot of difference. So that's the thermal coupling to the device, equally as important as the TEG itself that you have simulated and manufactured, as well as on the cold side. How do you get the heat out? The heat has gone in, but you want to maintain that delta T. So that can be done either with a air convective heat transfer, or you need to have active cooling itself with water. So this one is all about the thermal coupling. And once you have figured out how to fit all of this, you go also to match that incoming heat flux density into the device itself. So the device, I think most of you know, is all about matching the heat flux densities to the heights of the material as well as the fill factors. And that is how you determine, based on the thermal conductivity of the material, how tall your device is and how much of it are you filling up over here. So the fill factor is the ratio of the effective TEG material surface area to the exposed surface area. And there you can get to very unique TEG unicouples also, and that has been quite reported in literature. And when you look at the unicouple, whatever is remaining now has to be filled in with insulation, right? Whatever doesn't go through this material will go through from outside in. So that's why the insulation properties also start making a big difference. So that's the package. Insulation package as well as the optimum device design itself. Taking all these elements into it is how we also manufacture our materials. Here you can see a snapshot of our machines that we have manufactured ourselves. So this is the casting technology that we use for our silicon germanium materials and other silicon-based alloys, where we do batch casting of our materials, as well as a larger setup where the idea is to go into continuous casting of this material. We start with the melting. Alvise showed a picture of this where we melt the material, we cast it, we go through all the downstream processes. So this is all how do you process the material after it has been made in the right composition itself. You polish, you dice, you bond it. So this is quite important because our device now operates at 1000 degrees centigrade on the hot side. So we have to make sure that the bonding technology also survives these temperatures. So that's something we had to work on for a long time, how to figure that out. And then we test each one of these devices themselves. So we go through rigorous testing, which I will show you in the next slide. Here you can see a snapshot of this all silicon germanium based modules that I was talking about, where a 100 by 40 millimeter square module is able to generate 10 to 20 watts of electric. And this range is dependent upon the heat flux density, again, as I mentioned. What heat flux density you put in, and then what temperatures you end up with on the hot side. It's just a thermal equilibrium, right? We're able to string multiple of these modules together. So here you can see 15 to 20 modules to get up to 100 to 200 watts of electric. We also can do up to 1 kilowatt systems in cylindrical fashions. So here, our thing is that our main value proposition is that it's a unique TEG module design for radiative heat sources with the silicon germanium material. It is a solid state conversion technology, so that's one of the main advantages of thermoelectric generators. And this can also be tailor fit, so device shape as well as the surface for various incoming heat flux densities. Here you can see some of the kind of endurance tests that we have carried out. We have done 10,000 hour tests on the silicon germanium based module, where we have exposed the hot side to 750, 800 degrees centigrade to get up to the 2 to 3 kilowatt per meter square. We've also done thermal stress tests where we expose it to higher temperatures, so 1000, 1200 degrees centigrade, to make sure that the bonding and the entire module is still functioning. Our architecture itself is quite modular, so we can vary the height of the legs, which I told you is quite important based on the application, as well as the fill factors to interface with the available heat flux. Now, talking about applications. As I said, we have two main application scenarios. The first one was space, and this is where we have been working on for the last 5 to 6 years now. Here, a lot of the main keystone applications, as Antonio was mentioning in the past, this is one of the successful ones where thermoelectric generators were used in radioisotope power systems to power deep space satellites. Here you can see some examples from 1958 onwards, going towards the ones used on the moon, as well as the deep space ones going, which have crossed the solar system now, indeed. And these have also various power ratings. So from going all the way from, tens of watts to up to 300, 400 watts of electric in these systems. More recently, you might have heard of the ones from NASA, which went to Mars, which were based on lead telluride tags materials. Here, the power rating was 110 watts of electric, while the next gen RTG, which is again a system being developed along with NASA, where we are one of the partners, where we are making the silicon germanium materials, where the idea is to make up to a 250 plus watt of electric system. On this side of the ocean, ESA is developing a more compact system, so that's in tens of watts of electric, but coupled to a different fuel source. So here you see there are two changes: the power levels, as well as the fuel sources. So these are the two things that you have to couple together to get to the right system. And here, it also depends upon, okay, where do you want to finally use these radioisotope power systems? And one of the main use cases that we see that is coming up is systems for moon applications. Recently, they have discovered ice at the moon's south pole, and that is one of the main drivers to go and explore the polar region, as well as the permanently shadowed places where there is no solar flux, basically. but you still need to power any kind of lander, rover, and that is where radioisotope power systems could play quite a big role. In the last couple of years, there have already been 3 missions where the idea was to get to the moon and start exploring the moon's surface. But eventually, the landers had to be powered off and shut down when the lunar night came along. So that's basically two weeks of no sun. So solar panels don't work, and the equipment still needs to be kept warm as well as powered during that period. So they had to shut it off. So this is why we started also working together with qualified kind of fuels, such as the general purpose heat source, based on plutonium-238, which has been developed by NASA. So it's these blocks of fuel that you see over here, where, this has been qualified over a long period. But the idea is to get to a versatile system architecture which can tailor fit to this. So here you see examples of the unicouples, which can be varied based on what is the power level that is required for the final mission. So we have a simplified TEG architecture, which we use as a technological base. So this 100 by 40 millimeter architecture. And then we can tune it based on the incoming heat flux density from the radioisotope power field. One example of a project where we are developing this is along with the University of Dayton Research Institute in the US, where here again you can see this red GPHS block based on nuclear isotope material. And then the idea is to conductively couple it together with our TEGs to generate up to 14 watts of electric. So you start with 250 watts of thermal, and then you end with 14 watts of electric from a thermoelectric generator itself. So this is a concept that we are rapidly developing, and the idea is to get to the prototype and mature it as we go forward. Yep. So this is what we call a demonstrator. As I was mentioning to you, we perform simulations to tailor fit to the heat flux density. We do both thermomechanical as well as thermoelectric, because both of this is relevant for the final end use, whether you radiatively couple it or you do conductive coupling. Because so if you have conductive coupling, then the mechanical properties start to have a bigger impact in such a system. So you take in as inputs and constraints the heat flux density. Then you look at, okay, what the demands are, what is the power output. So then you look at what kind of temperature differential you can achieve in such a device. And then also the geometrical constraints, as well as the mechanical vibrations and other requirements. With that, these are some of the takeaways that we had from our exercise in the space applications. We want to have a thermogy solution, conversion technology for a pre-qualified nuclear isotope fuel architecture, where we are able to modulate what the device is to get to the power levels required, as well as the interface. So is it radiative, is it conductive, and to maintain a robust and simple architecture. We are able to do this quite quick. So now we have done this quite a few times where we simulate, we characterize what we need to put into the materials, as well as make a device in short periods. So we took all of our learnings in the space applications, and now the idea is to bring it to Earth, right? So bring space technologies to Earth, and then we identified 3 main application scenarios, which is the combined heat and power, the waste heat recovery, and as well as the heavy industry. So really high temperatures, corrosive environments. I think some of these kind of figures were already talked about in the morning. There are a lot of sources of waste heat in heavy industry. So they really take it up to high temperatures and they let it just cool down in air. And the idea was to take that heat and convert it into something useful for the industry itself that they can use downstream in their processing. In the micro CHP, as we call it, that's a combined heat and power application. The idea is to integrate our TEG modules in the boiler itself. So these are boilers which are used in houses to heat up their homes. And there, the temperatures can reach quite high, so 800 degrees centigrade and up. And then we can get the TEG modules to convert part of that heat into electricity itself. Here you can see some nice pictures of our TEG panels. So that's quite a large panel that we have tested at Tata Steel on top of their steel slabs, where we got quite close, as well as really high temperatures on the hot side to get power out of our devices. Here we have also worked with Elchem in their silicon manufacturing plant, as well as ArcelorMittal, where you can see what we developed was like a system to channel the heat towards our devices. One of our learnings from that entire exercise over the last few years is that this is basically, the TEG panel is a smart heat exchanger. So you get not only electric power, but you can also, with the silicon germanium material, get heat at a high temperature at the cold side. Because you operate this at a higher delta T, so you get temperatures at the backside of the TEG panel, which can be useful for the heavy industry. So if they need water at 80 degrees centigrade or even maybe steam, that is possible for these processes. Within the START project, as Alvise was saying, we start with a material which has been, basically mine waste material. And the idea is to cycle it to make it into something useful, and then finally get into a device which can be tested. And the main motivation that we had to get into this project was that from our experience, we had a material which was stable at high temperatures. And then when you look at the market, I think most of you recognize there's a material which is stable at really low temperatures, though composed of elements that are not commonly available, yes, tellurium. But in the mid temperature, from 200 to 50 degrees centigrade up to 600 degrees centigrade, there was quite a big gap in the literature itself. So we selected for the START project the waste heat from heat generation, the combined heat and power as the main driving application. And then we did the entire simulation exercise to look at, okay, what kind of architecture would be suitable with the START materials to get to the right powers. So here, I think this is a picture that Philippe had already shown. The sources of P-type tetrahedrites were collected from the waste sulfide mines and then mixed with the synthetic minerals. So it's a circular feed supply of raw materials. And we ended up with a P-type tetrahedrite. However, the N-type tetrahedrite does not exist yet with a suitable efficiency. So we combined it with a magnesium-based material in that device. We have gone through this chain now, and finally it took quite a long time, 2 to 3 years now, to figure out, okay, the milling properties which would be suitable, the sintering set points needed. As Patricia was saying, the sintering temperature as well as the pressures that we would need. So now we have a steady supply of material coming in from Genicore soon. And then we carried out an entire characterization exercise to see what would be the module sizes for the pellets itself to get to a suitable power. So we built up this model as well as collaborated along with Patricia, Constantina, to look at the mechanical properties of this device, because here, as we mentioned, the P-type and the N-type are not the same material. So the coefficient of thermal expansion starts playing quite a big role there. And that's something that we had to take into account of how we would be able to bond such a device. So we made the first devices. Now we are waiting for new materials where we have fixed the fill factors and the heights. We have tailor-fit, okay, what the thicknesses of the ceramic substrate need to be, as well as what the interfacial layer as well. So here it's around 1 to 2 microns in thickness, the interfacial layers. And that's something now we are testing to look at, okay, what the effect is of the roughness of the material on this interfacial layer robustness. We also optimized a low temperature bonding capability. So that's something which can be done quite at a low temperature, but then can operate at high temperatures in such a module. So in the coming last few months of this project, the idea is to make a few more of these devices and to test them in real world use cases. So that's in brief, the START project. We are also working in another Horizon Europe project where we are collaborating with CNR, who's leading the consortium. And the idea is to store intermittent renewable energy, so that's either obtained from concentrated solar power or photovoltaics in a high temperature thermal battery. As you can imagine, since it's intermittent, that means it's either during the day or in periods of the year where you have wind energy, right? And then, but use that energy when you need it in the household or in industries. So that's what we are working on. So the conversion of the heat through solid state converters to provide on-demand heat and power. So here you can see the inputs. We are working on the thermoelectric devices, also cascaded devices, so combining our silicon germanium devices with other low temperature devices to get to even higher efficiencies. And then finally, also testing the thermal battery, which is being developed within this project. The final one that I wanted to indicate towards was the Star Trek project, which is being led by CEA in France, where we are working along with them to mature the silicon germanium technology. In their case, they're working on additive manufacturing technology, while we are working on the cascade technology for the final end users. So these are all the end users that we are working with, where we get the requirements from them, so that we can integrate our device to get to the efficiencies that they would need for such devices. So here we are working with the heavy industry. So that's a steel manufacturer in Austria, as well as the boiler manufacturer in Austria to integrate our devices. Few key takeaways, both from the space as well as our terrestrial end users, is that we want to achieve a solution for the various temperature ranges. So it not only should operate well within the delta T, but also something that we can cascade together for even higher efficiencies. Within the START project, the aim was to get to something which can operate at 300 degrees centigrade with a stable material, and that is the quest that we have in this project. While in the high temperature, we have been working with silicon germanium materials, and that's the architecture I was showing you previously. So in the future, we want to develop such static solutions with high efficiencies of 9 to 10% or even higher, and then to put it into combined heat and power applications, because if it is just sole power, we see that is not the only selling point for TEGs. It is also a smart heat exchanger. So we need to offer this as a combined package. In space, as I mentioned, the idea is to integrate the most mature material and the module with a pre-qualified system. So that's the nuclear fuel system that I was mentioning to you. But make it modular for various power levels. That's the main target. Yeah. Here it just summarizes what I've been talking and presenting to you. We work in the power for extreme conditions. That's the space where we work along with Aerojet Rocketdyne as well as with ESA. The heat and power on location, so that's off-grid locations, where off-grid as well as combined heat and power applications, as well as developing new future technologies such as the cascade TEG and hybridizing along with TIG, which is thermionics. So that's in the PlaceTech project. So that's a Horizon 3 architecture that we are working on for even higher efficiencies. Yeah. Thank you for your attention, and open for questions.
Thank you, Ani.
Yep.
Are there any questions from the audience? No? It was clear. Thank you very much, Ani. Yeah. We'll pass to the next speaker.